Ladies and gentlemen, when we prepared this paper, we were not aware of the contents of Professor Ernst's paper. The good news for you is that this presentation is now going to be very short, very simple, and hopefully we'll get you to lunch nice and early. This paper is also about installation of pipelines through Reading, and as Professor Ernst stated, the integrity of the girth wells during this process is extremely important, not only for the successful operation of the pipeline subsequent to installation, but also for safety during the installation process. There was a major JIT run to address this issue, and this culminated in BMV publishing a document of the recommended practice F108 for the estimation of the defect sizes. This document is somewhat more simplistic than the methodologies presented in the earlier paper, but it is actually the basis with which tens of pipelines are being installed. Certainly all the projects controlled out of Europe and several out of the Americas are actually working from this document at the moment. So it is a very, very full document at the moment, and really most of what I speak about is going to be related to work we've done in relation to this document. Recommended practice F108 is based on engineering critical assessments performed at BS 7910, which I expect most of you are familiar with. This is a fairly traditional two-criteria approach where the possibility of failure is considered both from a plastic collapse and from a fracture perspective. And again, as indicated by Professor Ernst earlier, the JR curve, which is the input for the fracture part of the assessment, is based on the SEMT sample. This diagram is basically based on that developed by Nias and Laurier. And what we've tried to show here is that when we're in the LEFM regime, we can very well characterise fracture by a single parameter K, J, CTOD, and all our common geometries and structures will exhibit a fairly common toughness value. But as we move into the elastic plastic regime and approach general yield, we see certain geometries, the same specimen, and some structures such as a pipe in bending exhibiting a much higher toughness than we would actually expect from a compact tension or an SEMT sample. These are our traditional fracture toughness samples, and they're relatively low values because the practical plasticity is very heavily constrained by the compression zone at the back of the sample. And we don't get this with the SEMT sample, but the practical stress field is very, very much more representative of that which we're going to see in practice. I'm sorry, this is popped out. I hit the wrong button. This is a couple of JR curves from a fairly recent program we've been performing, which actually shows you an example of the sort of difference we get between the SEMB and the SEMT sample, which shows a very, very high level of conservatism. When we're working to F108, we limit the tearing to about 1 millimetre. And here, in this particular example, we see an almost factor of 4 difference between the SEMB and the SEMT performance. This is possibly higher than typical, but certainly a factor of 2 is very, very common. So we can see that the relying just on SEMB data without correcting for practical constraint will be very, very conservative. Just on the sort of practicalities of testing, which is probably more what the paper is going to be about, the sort of variances from traditional fracture toughness testing is we tend to hold the crack length plus pre-crack at around about 4 millimetres, irrespective of W. This is because we're typically simulating like a fusion defect, which is our most common defect. And a typical well pass would be about 3 millimetres, and then there's an additional 1 millimetre added on for conservatism. The other difference from traditional fracture toughness testing is that we normally test with B between B equals W and B equals W, rather than the opposite way around for conventional testing. But the most important factor is that we maintain W as close to the actual wall thickness of the pipe as possible, so The other practicalities of using this geometry are the fact that there's no well-defined rotation point, so we use a double click gauge to try and project out the sample surface. Because of the thermal loading from the grips and the sample length, we have to take a quite different approach to cooling than we would for traditional fracture toughness samples. And currently we're restricted to the traditional multi-specimen technique because the compliance curve tends to be very flat for these geometries, making sort of single specimen testing very difficult. There are two approaches we can take to the actual test. These are supposedly the fixed grip and pin-loaded options. The fixed grip system fits much nicely, more conveniently into a conventional testing machine, but at the moment, the NITA solutions for determining J are only available for a free span to width ratio of 10, and it's very, very difficult to maintain this ratio, especially for small values of W, when you're having to cool the sample, because typically we will test at a installation temperature, which certainly for Europe is normally taken to 0 degrees C. The pin loading option, or pivoted grip, is a little bit more difficult to configure in the first place, but both NITA and the compliance functions are independent of specimen length. This means we can test any length of specimen we like, and this makes it much easier to accommodate cooling. And I've managed to flip. Oh, sorry, I don't know why I'm using the end. We normally use electromechanical rigs for these. This is an example of a machine which will be going out to Italy soon to offer this testing over there. These machines have the advantage of nice long daylight for long loading chains, and they're also very good at holding the specimen at constant load during the prolonged cooling periods. This is just an example, a couple of pictures that show the pivoted grip systems that we use currently. The double click gauge system here, and cooling blocks to actually get the specimen down prior to it being insulated. Probably the most important thing we really wanted to say in this presentation was about validation. BS7910 was never really configured to address the situation of reverse cyclic plasticity, which Professor Ernst has explained is so integral to the rigging installation process. Because of this, there are concerns that the cyclic plasticity could adversely affect the load carrying capacity of the pipes and also affect the tearing resistance, and hence validation is required for each of the installation cases that we consider. The sample which is mandated at the moment is the segment sample, which essentially just resembles a large tensile sample with a semi-elliptical notch in the region of lowest toughness. The idea is that the second sample will be cycled and that the tearing resistance and load carrying capacity will be verified in a geometry which is more similar to the actual pipe. The reality actually is that the second sample is neither a very good test sample or a very good model of reality. The situation we model, because in a reading case we're predominantly strain controlled, we model the case of the strongest possible pipe against the weakest weld or an evenly matched weld. And this makes it quite difficult when we actually get the real sample to get adequate strain into the weld metal. The sample size, we can't get adequate width on the sample because it's coming up with curved pipe. In order to get the right balance between plastic lumps and fracture, we can't get the right acceleration of defects. And because these are always coming out of actual pipes, we're having to deal with misalignment, which complicates both the testing and the analysis. So for a couple of programs, we've actually advocated the use of cyclically loading the scent sample, very much as we saw in the earlier programs. And this gives us a much more direct indication of the effect of cyclic loading on both tearing and on load carrying capacity. And in terms of experimentation, it's certainly no more difficult than actually a segment test. We've taken a fairly simplistic approach. Obviously the first cycle is just analysed traditionally because it is no different from a standard scent test. We've then attempted to compress back to the original state, and then we've applied a second cycle, which has been analysed on a completely standalone basis because that's really very much akin to how the analysis is performed. We've got a slight variance here actually with the results of the previous speaker. As expected, the points from the first cycle agree exactly with the points from the straightforward monotonic curve because there is no difference at this stage. Interestingly, from the second stage, we actually see the points also falling very, very close to the JR curve, which is not quite in line with what we saw earlier. But at least both analyses do actually show that we haven't seen significant degradation in tearing resistance as a result of the cyclic loading. And if we take all of the crack driving energy, or tensile crack driving energy combined, we actually see the points rising above the standard JR curve. So basically, just to conclude, we would like to advocate the use of subject to additional work, the use of the cyclic scent sample as a validation for the ECAs until we start to see these more elaborate models that we discussed earlier this morning develop further, adopted on a widespread basis. Thank you.